Hello everyone, and welcome to another lecture in our march through the Transitions to Advanced Mathematics book. So the last section I talked about was regarding the Bolzano-Weierstrass Theorem, which said that, you know, it said something about accumulation points, and in particular it says every bounded infinite set of real numbers has a real accumulation point. And as has been the spirit of these lectures, especially on real analysis, we're going to now use that theorem in order to prove another theorem that's important in real analysis, which is the bounded monotone sequence theorem. So the key word here is sequence. So we talked briefly about sequences in section 4.6. So recall that a sequence is a function x whose domain is the natural numbers. And then you can spit out however you want. Yeah, you can spit out whatever the input may be and whatever the output may be. If the domain is a natural number, you're looking at a sequence. Denote nth term of sequence by x sub n. Okay, so hopefully this is all familiar to you. Bounded monotone, these are pretty much the same terms as we use for functions. So let's just get right to the definitions. So definition for a sequence of real numbers if there exists a real number b such that xn is less than or equal to b, and in parentheses here I'm going to put greater than or equal to b, for all natural numbers n, we say xn, sorry, not xn, we say xn is the nth term, x is the actual sequence, x is bounded above by b, and then in parentheses here I'm going to say bounded below to correspond to the parenthetical criterion. So let's just make that clear. So the parentheses corresponds to what's underlined in red, and then the things I'm underlining in blue correspond to being bounded above. Okay. So if you find a real number such that all the terms of the sequence are less than that number, then it's bounded above by that number, and similarly for if you find a number that's below all the terms of the sequence. The sequence x is bounded if and only if x is bounded below and bounded above. So a sequence can be bounded below without being bounded, and it can be bounded above without being bounded. But only if it's both bounded above and below do we say that it's bounded. Okay. So for example, if that's not clear to you, so for example, xn equals sine n is bounded, right? xn equals e to the n is bounded below by 0, for example, or even e to the first, but xn is not bounded because there's no upper bound. Okay, and so let's get straight to some results about this. I know you all are comfortable with these terms. We've talked about it several times. So theorem. A sequence of real numbers is bounded. This is a little bit obvious, but it's a theorem nonetheless. If and only if there exists a real number b such that the absolute value of xn is less than or equal to b for all natural numbers n. So let's prove this. This is a biconditional statement, so you have to go both directions. So proof. Assume the sequence x is bounded. Then there exists a b1 in the real numbers such that xn is less than or equal to b1 for all natural numbers n, and there exists a b2 in the real numbers such that xn is greater than or equal to b2 for all natural numbers n. Right? So we found the upper bound, we found the lower bound. Now let b equal to the maximum of the absolute value of b1 and the absolute value of b2. Then absolute value of xn is going to be less than or equal to b for all natural numbers n. So hopefully that's clear, but basically what you do is you find that because all the numbers are bounded above by b1 and all numbers are bounded below by b2, you can just take the maximum of those two in terms of absolute value, and basically you've created, maybe I should just draw a picture here. So say you have b2 here and b1 here, and then all of x is just right in here. And if b2 and b1 are both positive, then you just take b to be b1 and you're done. But in the case that b2 is negative, you have to look at the absolute values, and then once you've done that, you've established that all of xn is has the following property. Right? Okay. So I mean, this is drawn without loss of generality. So that's one direction. Now assume the absolute value of xn is less than or equal to b for all n. Then negative b is less than or equal to xn, and xn is less than or equal to b for all natural numbers n. So xn, it's not xn, sorry, x is bounded. This is the easier direction. It just follows immediately from what it means for the absolute value of x to be less than or equal to b. Okay, so that's one result. Let's go to another one. Theorem. If a sequence of real numbers converges, then it is bounded. Okay, so this is not a biconditional statement, so it's just a unidirectional proof. But if you have a sequence that converges, then it must be the case that it's bounded. So let's prove this. X is a convergent sequence. Say it converges to L in the real numbers. Then, for every epsilon greater than 0, there exists a natural number n such that if you take the terms of the sequence that are farther along than that capital N, the absolute value of xn minus L is less than epsilon. So you can do this for any epsilon. So let's choose an easy one. We can't choose 0 because epsilon has to be bigger than 0, but we can choose our next favorite number. So let epsilon be equal to 1. Then there exists an n star in the natural numbers such that if n is bigger than or equal to n star, we have that the absolute value of xn minus L is less than 1. We have that the absolute value of xn minus L is less than 1. Okay, and this is true for all n greater than n star. Now there is a property that says the following: the absolute value of xn minus the absolute value of L, and you take the absolute value of that, is going to be less than or equal to the absolute value of xn minus L. This is a standard absolute value property. Therefore, for all n bigger than or equal to n star, we have the absolute value of xn in absolute value minus the absolute value of L is less than 1, which means minus 1 is less than the absolute value of xn minus the absolute value of L, and that's less than 1. Which means for all n bigger than or equal to n star, the absolute value of xn is less than the absolute value of L plus 1. So all the terms above n star, in sequence are all less than the absolute value of L plus 1. We have a finite number of terms left, namely the sequence terms up to n star. So let b be equal to the maximum of x1, x2, all the way up to x n star minus 1. Then xn, the absolute value of xn is less than or equal to b for all natural numbers n. So x is bounded. So yeah, pretty cool result about sequences. Well, what kind of things can we say about sequences that converge? Okay, but moving on. So we defined bounded. We looked at some properties of bounded sequences. Now let's look at monotone sequences. And this again corresponds to maybe what you've studied in terms of functions, increasing or decreasing. So let x be a sequence of real numbers. The sequence x is increasing, and I'm going to put decreasing in parentheses. If and only if for all nm in the natural numbers, sorry, I don't know why I put parentheses there. If n is greater than m, then xn is greater than or equal to xm, and in parentheses xn is less than or equal to xm. So it's increasing if as you move further down the sequence, you get bigger and bigger numbers, or it's decreasing as you move down the sequence, you get smaller and smaller numbers. The sequence is monotone if and only if x is either increasing or decreasing. So one or the other. Obviously, I mean, it can be both if it's just a constant sequence, but yeah, if it's either one of these is true, then it's a monotone sequence. And you prove that a sequence is increasing or decreasing pretty much the exact same way that you do for functions. So, example, prove xn equals n over n plus 1 is increasing. So suppose n, m are natural numbers with n less than m. Then, what can we say? We say that m times n plus n is less than m times n plus n. So I'll let you think about what I multiplied on both sides here. Yeah. what did I multiply on both sides here to get this result? Which tells me that n times m plus 1 is less than m times n plus 1, which tells me n over n plus 1 is less than m over m plus 1, which means the sequence is indeed increasing, right? Okay. So now let's go to the main theorem of the section. So the bounded monotone sequence theorem. So what does the theorem say? For every bounded monotone sequence X, there exists a real number L such that the limit as n goes to infinity of xn equals L. And there's a nice intuition for this, so just imagine you have a bounded increasing sequence, so it's monotone, so decreasing is completely analogous. But so I'm just going to write intuition here. So say you're looking at n, and then on the y-axis you're plotting xn, and you're plotting a bounded sequence, but it's monotone. So say that means you can draw basically the entire sequence between these some two horizontal lines like this. And so the sequence is going to increase and increase and increase, but it's bounded, so it has to get arbitrarily close to its upper bound. And we claim that this should be L, right? Okay, so now let's prove it. And again, it's completely analogous intuition for when it's decreasing. So assume the sequence X is bounded and increasing. And again, it's completely analogous for if it's decreasing, so you just change some inequalities around. And if the sequence is finite, there's really nothing else to say because you just take the biggest of the terms in the finite sequence. So suppose the sequence xn such that n is taken from the natural numbers is infinite. Okay? Then, by Bolzano, I think I spelled this wrong. There's an E here. Weierstrass Theorem. The bounded infinite set xn has an accumulation point. Call it L. So claim xn is less than or equal to L for all natural numbers. If not, then there exists an n in the natural numbers such that x sub n is greater than L and x sub n is greater than L for all n greater than or equal to n, big N. Since L is an accumulation point, for xn such that n is greater than or equal to n. And here's something to think about. So notice in the original statement of the theorem we said L is an accumulation point for this set up here, but I claim that L is an accumulation point for this set, which is for this boxed set, which is not the same as the one I circled above here. So try to prove this. As my pencil stops working, so prove this. But anyway, it's an accumulation point for that set. So since L is an accumulation point for that, let delta be equal to the absolute value of xn minus L. Then the delta neighborhood of L contains no points of the set xn such that n is bigger than or equal to n. And this is a contradiction because it contradicts the idea that L is an accumulation point. Remember, that means that every delta neighborhood, no matter what you take delta to be of L, must contain infinitely many points from the set for which it's a accumulation point. Thus, xn is less than or equal to L for all natural numbers n. Okay. So next we claim x converges to L. Let epsilon be greater than 0 be given. Since L is an accumulation point, of the set xn such that n is in the natural numbers, there exists a natural number m such that what? Such that xm is an element of the epsilon neighborhood of L. That is, L minus epsilon must be less than xm. So, for n bigger than capital M, L minus epsilon is less than whatever that xm is, which is going to be less than or equal to xn. And why? Because remember, we're looking at a increasing sequence, and I've taken n to be bigger than m, which means xn must be bigger than or equal to xm. So xn is bigger than that, And we proved that this is less than or equal to L, and now I can just say that's less than L plus epsilon. Therefore, for n bigger than m, xn minus L is less than epsilon. Thus, limit as n goes to infinity of xn equals L. And that's really the conclusion to this section. We just proved another important theorem. And as you go through these lectures, I want you to realize that we're kind of doing a circular thing. We started off assuming the reals were complete, and using that, we proved the Hein-Borel theorem. And from the Hein-Borel theorem, we proved the Bolzano-Weierstrass theorem. You know, about bounded sets of real numbers have infinite bounded sets of real numbers have an accumulation point. And then the Bolzano-Weierstrass theorem, we were able to establish this bounded monotone sequence theorem. And then to finish off this chapter, we're going to use the bounded monotone sequence theorem to again prove that the real numbers are complete. So it's kind of a circular sequence that gives you a nice introduction to the real numbers. So I hope you'll look for that. Probably I'll post it this weekend because the end of the semester is on Monday. But thanks for listening, and I will catch you later.